Hello everyone, my name is Yoshihiko Suzuki from Japan. First of all, I appreciate Yan Lee for inviting me to this good opportunity. My talk is entitled Koopman Operator Techniques in Data-Driven Power Systems Technologies. Since 2008, with many collaborators, I have worked on the use of Koopman operators for analysis and control of nonlinear dynamics in power systems. In this talk, I'd like to briefly introduce our efforts on Koopman operators for nonlinear analysis of power systems. First of all, let me introduce the motivation of recent research. This research is motivated by the development of sensing and data collecting technologies in power systems. Recent advance of sensing technology and ICT enable us to obtain massive quantities of data on power system dynamics. As you know so much, PMU and WAMs are widely recognized in these technologies. In this situation, it is very important to use such massive quantities of data for analysis and control of nonlinear power systems. I use nonlinear power systems, meaning that we consider a nonlinear dynamical system model to represent the dynamics of power systems. Many groups of researchers have worked on the use of data such as voltage, phase, power flow, and power demand. As far as I looked for, most of the literature used based on linear dynamical systems that are easy to analyze, control, and identify. So the use of nonlinear dynamical systems is challenging in the research of power system data analytics. This problem is translated in the systems and control, how we grasp dynamic characteristics such as stabilities of nonlinear power system models from a finite set of output timesheets. Also, in applied math, the same problem is translated as what the mathematical framework that connects the nonlinear dynamic system with its observations. In this talk, I'd like to introduce our efforts on the data-driven analysis of power system dynamic performances. For this, we have focused on the application of Koopman operator theory for nonlinear dynamic systems. Koopman operator is a linear infinite dimensional operator defined for a large class of nonlinear systems. Interestingly, this Koopman operator is capable of capturing the full information on the underlying nonlinear systems. The contents of my talk are listed below. First of all, I'd like to briefly introduce what is Koopman operator, what are spectral properties of Koopman operator. After this, I'll give one concrete data-driven application on stability assessment. By doing so, I described how Koopman operator techniques are used to solve a realistic problem in power systems directly by data. Okay, in the following 5 slides, let me briefly introduce the basic notion of Koopman theory. For this, now we consider the following nonlinear dynamic system in discrete time. Here, K is a discrete time, X is the state of the system, and capital Rn is a state space. Also, capital T is a nonlinear map that describes the rule of how X evolves in time. In the standard dynamic system theory, we have focused on the time evolution of states X under the systems. On the other hand, in Koopman operator theory, we focus on the time evolution of output or observable of the system. Here, the y sub k is the output of the system at discrete time k and is given by a function f of state. This function f is a map from the state space to the real line and is called the observable. This is a mathematical model of measurement or observation of the dynamic systems. In Koopman operator theory, we focus on the time evolution of observables under the systems. Okay, now consider the time evolution of the state from x0, x1, and x2. For estimating the time evolution of output under the time evolution of x, now we introduce observable f, and then we map each state by f, and then we obtain the time evolution of outputs from y0, y1, and y2. This is the standard idea for estimating the time evolution of outputs. In the Koopman operator theory, we don't consider the state directly. Instead of this, we consider the time evolution of the observable f under the dynamical system capital T. This corresponds to the composition operation of f with the nonlinear map capital T. In this, we are able to derive the same time evolution of output y0, y1, and y2. This composition operation is mathematically denoted by the so-called Koopman operator capital U. Okay, this is again the definition of Koopman operator U for the dynamical system T. Here I'd like to mention three main benefits of the use of Koopman operator for nonlinear systems and nonlinear problems. The first one is that this operator capital U is linear in the space of observables, function space. So in terms of these linearities, we can conduct analysis, control, and design of original nonlinear system T. In this point, the spectral properties of Koopman operator play a dominant role in the research on nonlinear dynamics. I will introduce this point in the next page. The second one is that the use of Koopman operator is effective for handling large-scale problems. The third one is that the Koopman operator is pretty direct to the data-centric application, which is the main concern in this talk. Okay, now regarding the first and third points, let me introduce the spectrum of the linear Koopman operator. This Koopman operator acts on a function space and is generally infinite dimension. So it has not only discrete spectrum but also continuous spectrum. But in this talk, it is enough to introduce a brief idea of discrete spectra, so I'll skip the continuous part of this spectrum. This discrete spectrum is a natural extension of eigenvalues, eigenvectors in a finite dimension matrices. The eigenvalue lambda I and associated eigenvectors, in this case eigenfunction phi I, are defined as follows. As a simple examples, now we consider the finite dimensional LTI system in which capital A is a square matrix or system matrix with size n. Then we consider left eigenvector ui and associated eigenvalue lambda I of A. By doing so, we can find the eigenfunction of the Koopman operator for the LTI system as follows. The proof of this is straightforward. See the last line of this page. The discrete spectrum of the Koopman operator is used for the mode decomposition of nonlinear time series, called the Koopman mode decomposition KMD. So in the next page, I'll introduce KMD. This is the relevant idea in which we decompose multi-dimensional nonlinear time sheets in terms of eigenvalues and eigenfunctions of Koopman operator. Now we consider the situation in which we have multi-outputs y1k to ymk at discrete time k. The multiple outputs are modeled by the multiple observables f1 to fn. Their time evolutions are described by the Koopman operator capital U. By direct calculation, we obtain the following expansion of multi-dimensional outputs in terms of eigenvalues lambda I and eigenfunction phi I of U. This last vector vi in complex value is introduced as a coefficient for the decomposition. That is called the Koopman mode. Here, the discrete time k just appears as the kth power of the constant Koopman eigenvalue, which are complex numbers. Therefore, this implies that KMD decomposes nonlinear time series into the infinite set of single frequency modes. Finally, let me introduce how KMD is conducted for time series data. There are many methods proposed in literature which we generally call the dynamic mode decomposition, DMD. One idea is called the analytic type algorithm that was proposed in 2009. For given finite data f0 to fn on dynamics of outputs, by using these algorithms, we can derive the following decompositions that are computationally easy from the time series. The data at the time k, fk, are decomposed into the finite set of modes with single frequency oscillations. The numerical outcomes lambda tilde I and capital V tilde I are similar to the Koopman eigenvalues and Koopman modes. We will use these algorithms in this talk for obtaining the numerically Koopman eigenvalues and Koopman modes. Okay, the mathematics now are over. We will move to the first data application in the stability assessment. This is a joint work with Professor Igor Mezic in UCSB. Okay, this slide provides the motivation behind the current topic, 2006 nationwide disturbance occurring in UCT grid. The UCT grid is a synchronously connected 60 Hz power transmission network in Europe from Spain to Germany. No power of 70,000 megawatts was supplied due to this disturbance. This disturbance resulted in the separation of the UCT grid into three areas: yellow, green, and blue as shown in the right figure. This figure shows the data on power exchange deviations of 8 areas in this grid: Belgium, Switzerland, Spain, and so on. The power exchange deviation is the difference of actual power exchange and scheduled one in each area or in each country. You can see that the power exchange deviations oscillate in a complicated manner and gradually grow as time increases. After the last time in the left figures, a single local control action in Germany initiated the cascading failure in this grid and its separation into the three areas. Here in the official final report, we can find the following sentences. These transient deviations are the result of a global shift in the physical power flows within the UCT synchronous grid area to change in the generation programs and exchange programs around 22. These curves show a situation which is rather normal and typical at that time. But after the time shift, in the left figures, one single local control action destabilizes the large-scale grid. So now we can say the dynamics observed here were potentially unstable or under the loss of n-1 security of power transmission. Our current question is that how do we detect the precursor to the grid's instability before the occurrence of it? Okay, this is a problem formulation for the data-based assessment of stability and instabilities. We have the data on power flows at M sites or M transmission lines. Normally, we consider the stability of a per system based on the state equation like here. And then X is the state of the system including the voltage and the phase. Capital T is a nonlinear map of per system dynamics. Here we can say that it is very hard for us to construct mathematical models that accurately capture the dynamics of the entire UCT grid. From this setting and motivation, we can state the problem as follows. Determine the stability of the persystem using the power flow data without any development of models. The important question now is, how do we associate the data on power flow with the nonlinear models? Because the nonlinear model has information on the stability of the system. In Koopman operator theory, we have the clear answer on this. It is enough to model the power flow as a vector-valued observable defined on the state space of the persistent models. Then, we investigate the dynamics of power flows in terms of the Koopman operator, in particular Koopman eigenvalues and Koopman eigenfunctions. So in the same manner as the Koopman mode decomposition, we can decompose a vector-valued observable F flows as follows. This is clearly connected to the time series data on power flows as follows. Here, lambda I is again the Koopman eigenvalue that capture the stability of the state's dynamics. Then, the stability assessment based on the power flow data is proposed as follows. It is enough to evaluate the Koopman eigenvalues computed from the power flow data. Of course, by using the analogy type algorithms, we can do this analysis for the finite number of approximations of eigenvalues from finite time data. Okay, now apply this assessment to the finite time data on power exchange deviations. In this slide, this figure describes the distribution of the Koopman eigenvalues computed from the fall data. In this figure, you can see that most of the eigenvalues are placed close to the unit cycle. But one pair of eigenvalues exists outside of the cycle. In other words, one unstable mode emerges in the dynamics of the UCT grid. This emergence is a dynamical evidence of the time-growing instability of power exchange deviations observed in the fall data. Next, we apply this assessment to pairs of the data and consider the dependence of the eigenvalue distribution on data length. From now, I show the movie of how the distribution of unstable eigenvalues change with the data length. As the data lengths increase, the eigenvalue distribution changes, but the unstable mode pair discussed in the left figure is frequently excited. In fact, this figure is a histogram of the emergence of unstable eigenvalues from many different data lengths. The red color shows that many eigenvalues are repeatedly emerged. From these figures, you can see that the excitation of the unstable mode before the onset of the disturbance. This implies that the normal and the typical situation mentioned in the final report has been potentially unstable. This disturbance might be inevitable. This is not a good consequence of the Koopman operator-based data-driven assessment, but we can use this sort of assessment for evaluating the security of supply. That is, we anticipate the potential instability from the currently stable system to avoid it directly from the data. Okay, next is the ending of my talk. So in this talk, I presented our effort on Koopman operator techniques applied to analysis of nonlinear dynamics occurring in a power systems. My message is simple and clear. The Koopman operator theory enables the development of fully data-driven methodology and tools for nonlinear power systems. The ongoing work in my group are robust mode estimation with connection, integration of Koopman operators and machine learning, and real-world implementation of our products. There is a part of the list of application of Koopman operator techniques in systems. You can see that the applications are currently diverse and still developing, such as voltage analysis, prediction design, load forecasting, and so on. This is a recent book published by my collaborators, Professor Alexander Mauroy in Belgium and Professor Igor Mezic, UC Santa Barbara. I hope it will be help to our audience who are interested of our approach based on Koopman operator. That's all I have. Thank you for your kind attention.